Hi, today I'm going to be talking about the characterization of putative cellulase genes from Rumen Switchgrass microbiome. What is cellulase and why is it important? Well, first let's talk about biofuel production. Biofuel production has become an important area of research since it provides an alternative for renewable and green energy sources while reducing carbon footprint. This takes advantage of the abundant plant material available in nature. Biofuel production requires cellulose hydrolysis by cellulase. Cellulase is a class of enzyme that degrades cellulose into simple sugars, which can then serve as feedstock for microorganisms and be turned into biofuel. However, this process on an industrial scale has been inefficient so far, and this is due to the high cost and low activity of cellulase currently available. In order to search for potential cellulase with higher activity, Hess et al. Did a metagenomic studies and sequenced genes from the microbiome community found in Rumen switchgrass. They found over 27,000 pure carbohydrate active genes and aimed at characterizing the functions of these genes. 90 genes were expressed and 51 genes were found to have cellulase activity. We follow up on the work of Hess et al. By characterizing some of these putative cellulase genes found. Our group in particular focused on three genes, HiSig 150, 460, and 380. This is an overview of what we did in our Chem 131B class. First, we extracted DNA from Rumen switchgrass. Then, we generated gene insert with design primers via PCR. We did restriction digest with SSP1 for our empty vector PET His6 tab. Then we inserted our genes into the linearized vector via Gibson assembly. This was followed by transformation and expression. After that, we did purification under denaturing condition and dialysis for our sample. We tested for cellulase activity using congruent assay, and we also did differential scanning fluorometry or DSF analysis in order to analyze the folding of our protein. This is what our results looked like. After Gibson assembly, we did colony PCR in order to determine if we have any successful clones or not. Our gene HiSig 150 and 460 were 1269 and 1281 base pairs long respectively. We didn't see any single bands near the target length region for all of our colony PCR products, and we concluded that our cloning attempts were unsuccessful. This was indeed confirmed by sequencing data. The only successful clones were from gene HiSig 380 from group 3 coli, so we used these clones for the next steps. Also, via sequencing data, we found some mutations in our clones for HiSig 380. We found two silent mutations and one missense mutation changing tyrosine to histidine residue. Tyrosine and histidine are both slightly electronegative, and they also both have an aromatic ring. So we proposed that this mutation would not have too much of a dramatic effect on our protein function, although we actually were not so sure about this. Due to time constraint in our class, we decided to move on to the next step anyways. After transformation, we induced protein expression with IPTG, and in our SDS page analysis, we found that our target protein, which weighed about 42.7 kilodalton in the insoluble fraction instead of the soluble fraction as expected. For this reason, we had to purify our protein under the denaturing condition, and we did that via nickel anti-affinity chromatography. This is the SDS page result of what that looks like. We observed two bands near the target weight in the elution fractions, as you can see here. Out of these two bands, the top one looked slightly thicker in illusion D1, D2, and E1, and the bottom band looked slightly thicker in illusion E2. Since we were not sure which band had our target protein, we decided to combine D1, D2, and E1 illusion into one sample, and we analyzed this alongside E2 in the next steps. Our D1 through E1 sample and E2 sample were both dialyzed in monosodium disodium buffer at pH 8.01 with DTT, and we did this in order to refold our proteins. After dialysis, we tested for cellulase activity with conglomerate assay. Here, the top quadrant had our E2 sample and the bottom quadrant had D1 through E1 sample. Both samples show no cellulase activity against CMC or carboxymethyl cellulose substrate. We also saw a white dot on the plate, but that was likely due to a lump in the agar gel. We were curious to see if our proteins were successfully refolded via dialysis or not, so we did the SF analysis afterwards. We used lysozyme for our positive control and our frozen undialyzed E2 sample for our negative control. Since our lysozyme curve looked quite different from what we expected, we compared our data with group mac and cheese, and we found that the fluorescent intensity curve for both of our samples, dialyzed D1 through E1 and dialyzed E2, they both look similar to the negative control instead of the positive control, and from this, we concluded that our dialysis attempt was unsuccessful, and unfortunately, our protein samples were not refolded. For this reason, we could not actually determine if our genes were cellulase or not. Since dialysis was a major step in our experiment and we failed at that step, this could be improved upon by testing with different buffers at varying pH values. Since our genes were extracted from Rumen Switchgrass and we were not sure about the characteristic. We could also add crowding agents so that protein can refold in a better environment. And despite our unsuccessful attempt at characterizing these putative cellulase genes, the work of Hess et al. Remains useful for discovering new cellulase because there were still thousands of genes waiting to be characterized. And this ongoing research to search for cellulase with high efficiency is still crucial for improving biofuel production on an industrial scale. These are my references. And finally, I would like to thank the Department of Chemistry at SJSU for providing us with a great opportunity to collab with Hess et al. And even when our attempts were unsuccessful, we learned a lot in this class. I would also like to thank Dr. Wang for being such an amazing professor and for her amazing guidance in our journey. We had a lot of failed attempts and a lot of failed experiments, so I think she did a really great job at guiding us through all the struggle that we face. I also like to thank Dr. Carol for her help in our DSF analysis. And finally, I want to thank everyone in Chem 131B class for being such good sports throughout the whole semester. And also, thank you for listening to my presentation. Have a good day.